Hello there, and welcome to the Silent Science. I'm glad you've joined me tonight, or today, depending on where you were in the world before we drift into the glowing heart of our favorite neighborhood star. I'd love to know where you're listening from. And what time is it where you are? Are you tucked into bed, ready to unwind, wrapped in a blanket on the couch? Or maybe just letting this play quiet while your cat carries out a secret mission in the shadows? If you're enjoying these gentle voyages through the cosmos and the curious corners of science, a soft tap on the like button and a kind subscription truly means a lot. It helps keep this sleepy little channel shining bright. Now, tonight's story is about a star that never sleeps, quite the opposite of this channel, really wild. The sleepy scientist is here to help you wind down and switch off. The sun is always on, always burning. Asterisk. The sun, a never-sleeping beacon in the sky. Imagine a star so vast, so powerful, that it has been burning for over 4 billion years, and yet it shows no sign of slowing down. This is our sun, the radiant heart of our solar system, the quiet engine that fuels life on Earth and keeps our world bathed in warmth and light. It rises without fail each morning, casting golden rays across fields, oceans, and cities alike, and sets just as reliably in the evening, leaving behind the soft glow of twilight. But beneath this familiar rhythm lies an astonishing truth. This celestial body we see every day is not merely shining. It is alive with constant, invisible activity. A cosmic furnace where matter is transformed into energy through nuclear fusion. Every second, deep within the sun's core, millions of tons of hydrogen are converted into helium, releasing an immense amount of energy in the process. This energy, born from the violent collisions of atomic nuclei, takes thousands to millions of years to make its way from the center of the sun to its surface, only to burst forth at the speed of light and travel across space to reach us. That warm glow on your skin, the light filtering through your curtains in the morning, even the very air you breathe, all of it owes its existence to this delicate balance of forces happening 93 million miles away. Tonight, we embark on a gentle journey through the heart of our nearest star. We will explore how nuclear fusion sustains the sun's brilliance, how its layers work together to release light and heat, and how its influence extends far beyond mere illumination. From the quantum mechanics that allow protons to overcome their natural repulsion to the magnetic storms that dance across its surface, we will uncover the intricate processes that keep our sun shining. So, settle in, let your thoughts drift like stardust, and prepare to marvel at the silent science behind the star that never sleeps. The birth of a star. Long before the sun took its place as the steady beacon in our sky, it was nothing more than a drifting cloud of gas and dust, adrift in the vast darkness of space. About 4.5 billion years ago, this molecular nebula, cold, dense expanse of mostly hydrogen, with traces of helium and heavier elements, began to stir. Something, perhaps the shock wave of a distant supernova, or the gravitational pull of passing stars, nudged this quiet patch of interstellar material into motion. Slowly at first, then faster, the cloud began to collapse inward under its own gravity. As gravity pulled the particles closer, the cloud began to spin, flattening into a disk, with a dense central region forming at its heart. More and more mass accumulated, increasing pressure and temperature, until, finally, the core reached a staggering 15 million degrees Celsius. At this point, something remarkable happened. Nuclear fusion ignited. Hydrogen atoms, stripped of their electrons by the extreme conditions, began fusing into helium, releasing an immense amount of energy in the process. This was the moment the sun truly came to life, marking the transition from a collapsing cloud of gas to a fully formed star. But fusion did not happen all at once. In fact, the process was surprisingly slow, relying on a strange quantum phenomenon. known as tunneling, to overcome the natural repulsion between positively charged protons. Without this odd quirk of physics, fusion would be impossible, and the Sun would have remained nothing more than a failed protostar. Instead, the reaction took hold, creating a self-sustaining cycle where the outward pressure from fusion balanced the inward pull of gravity. With this equilibrium established, the Sun settled into its current state, a stable, glowing giant that would go on to shape the fate of everything in its orbit. The quantum dance of fusion deep within the Sun's core, where temperatures soar to 15 million degrees Celsius and pressure crushes matter with unimaginable force. Hydrogen atoms exist in a state unlike anything we encounter on Earth. Stripped of their electrons, they form a dense plasma of bare protons, constantly colliding with one another at incredible speeds. Yet, despite these extreme conditions, fusion does not occur as easily as one might expect. Protons, both carrying positive charges, naturally repel each other, much like two magnets pushed together with their same poles facing. For fusion to take place, these protons must come close enough for the strong nuclear force, the fundamental force responsible for binding atomic nuclei, to take over. But how do they overcome this formidable barrier? The answer lies in one of the most fascinating quirks of quantum mechanics: tunneling. In classical physics, if a ball lacks the energy to roll over a hill, it simply rolls back down. But in the quantum realm, particles behave more like probability waves than solid objects. Occasionally, a proton doesn't need enough energy to climb over the repulsive barrier. It simply vanishes from one side and reappears on the other, as if it had tunneled through the obstacle. Though rare, these events happen often enough in the Sun's massive core that fusion occurs continuously, ensuring a steady supply of energy. When two protons successfully fuse, one of them undergoes a transformation. Through the weak nuclear force, one of the four fundamental forces of nature, it converts into a neutron, releasing a positron, the antimatter counterpart of an electron and a neutrino. What remains is a deuteron, a nucleus containing one proton and one neutron. This deuteron quickly encounters another proton, fusing again to form helium-3, a lightweight version of helium with two protons and one neutron. Finally, two helium-3 nuclei collide, producing a stable helium-4 nucleus, while releasing two spare protons that return to the pool of available hydrogen. This entire process, known as the proton-proton chain, is the dominant fusion reaction in stars like our Sun. And though it may seem simple in theory, the reality is anything but. Every step depends on precise conditions, and even the slightest imbalance could disrupt the delicate equilibrium that allows stars to shine. Yet, despite its complexity, this chain reaction has sustained the Sun for billions of years, and will continue to do so for billions more, ensuring that the light reaching Earth today began its journey long before human civilization even existed. The long journey of light, once energy is released in the Sun's core through nuclear fusion. It begins a long and winding journey toward the surface. But this journey is anything but direct. The photons created during fusion, teeny packets of light, do not shoot straight out into space. Instead, they embark on a chaotic, meandering path through the dense plasma of the Sun's interior, bouncing from particle to particle in a process known as radiative diffusion. Imagine being a photon newly born in the core, eager to escape into the cosmos. You try to move forward, but within a fraction of a millimeter, you collide with an electron and are absorbed. A fraction of a second later, you are re-emitted in a completely random direction, perhaps back toward the core, maybe sideways, or if you're lucky, slightly closer to the surface. This process repeats endlessly, sometimes for thousands or even millions of years, as you zigzag through the Sun's radiative zone, in this layer, which extends from about 25% to 70% of the sun's radius. The density is so high that photons can barely travel before encountering another particle. Each interaction slows their progress, making their escape frustratingly slow. Over time, however, some photons gradually make their way outward, losing energy with each collision. By the time they reach the outer edge of the radiative zone, many have degraded from high-energy gamma rays into lower-energy forms of light, such as visible or infrared radiation. Eventually, these photons enter the convective zone, where the rules of energy transport change dramatically. Here, the plasma is cooler and less dense, making radiative transfer inefficient. Instead, the sun relies on convection. Massive bubbles of hot plasma rise toward the surface, cool slightly, and sink back down, forming enormous churning currents that carry energy upward much more efficiently than radiation alone ever could. These convective cells, some spanning hundreds of thousands of kilometers, churn slowly but steadily, ferrying energy from the depths of the sun to its outer layers. Finally, after an arduous journey lasting anywhere from 10,000 to over 1,000,000 years, the photons reach the photosphere, the visible surface of the sun. Here, the plasma is thin enough that photons can escape into space without immediately being reabsorbed. Once free, they race outward at the speed of light, covering the 93 million mile distance to Earth in just over 8 minutes. When they arrive, they illuminate our world, power photosynthesis, and provide the warmth that sustains life. It is humbling to realize that the sunlight we experience today may have begun its journey when mammoths still roamed the earth, or when glaciers were carving valleys into the landscape. The sun's energy, though seemingly instantaneous in its arrival, carries with it the echoes of ancient reactions occurring deep within our nearest star, the ghosts of the sun, neutrinos, and their silent journey among the countless particles produced. In the sun's core, few are as elusive or as important as neutrinos, born in the very first step of the proton-proton chain. These ghostly particles slip through matter with almost supernatural ease, traveling undisturbed from the sun's core to the farthest reaches of space. Unlike photons, which take thousands to millions of years to escape the sun, neutrinos make their exit in mere seconds, slipping past the dense plasma and emerging into the void, as if the sun itself were made of nothing at all. Each second, trillions upon trillions of these nearly massless, electrically neutral particles pass through your body, through the walls, the air, the entire planet, without so much as a whisper of interaction. They are the universe's most skillful escape artists, moving through lead, stone, and flesh as though they were empty space. In fact, it would take a block of lead a light-year thick to stop just half of the neutrinos streaming from the sun. And yet, despite their near-invisible nature, these particles serve as messengers from the heart of our star, offering scientists a direct glimpse into the nuclear fusion that powers it. For decades, neutrinos puzzled physicists. Early detectors built to observe them found only about a third of the expected number and enigma known as the solar neutrino problem. Did our models of the sun's core misrepresent fusion rates? Or was something else happening to these mysterious particles along their journey? The answer lay in a discovery that would reshape our understanding of particle physics: neutrino oscillation. Neutrinos come in 3 different flavors: electron, muon, and tau. They have the peculiar ability to shift between these identities as they travel. The early detectors, designed to capture only electron neutrinos, were blind to the others. As neutrinos streamed from the sun to Earth, many changed flavor mid-flight, evading detection and giving the illusion that they had vanished. Once this transformation was understood, new experiments confirmed that the sun was indeed producing the correct number of neutrinos all along. Beyond solving this mystery, Neutrinos offer scientists a unique window into the sun's inner workings. Because they interact so rarely with matter, they emerge from the core virtually unchanged, carrying with them direct evidence of the fusion reactions taking place there. While photons take eons to reach the surface, neutrinos arrive almost instantly, providing real-time confirmation that the sun continues to burn steadily. In this way, they serve as silent witnesses to the process that lights our skies and warms our world, reminding us that even the most hidden corners of the universe can be explored if we know what to look for. The delicate balance, gravity versus pressure at the heart of every star lies a cosmic tug-of-war, a battle between two colossal forces: gravity, which relentlessly pulls matter inward, and pressure, which pushes outward in response to the immense energy released by nuclear fusion. This delicate balance, known as hydrostatic equilibrium, is what keeps the sun stable, preventing it from either imploding under its own weight or bursting apart in a catastrophic explosion. It is the reason the sun shines steadily, rather than flickering unpredictably or collapsing into darkness. Gravity, the sculptor of stars, played a crucial role in the sun's formation. Billions of years ago, it drew together clouds of hydrogen and helium, compressing them into a dense, scorching core. As the core grew hotter and denser, fusion ignited, unleashing a flood of energy that generated outward pressure. This pressure, in turn, resisted gravity's inward pull, creating a dynamic equilibrium. If fusion were to suddenly cease, the pressure would drop and gravity would win, causing the core to contract and heat up until fusion reignited. Conversely, if fusion somehow accelerated, the increased pressure would cause the core to expand and cool, restoring the balance. This self-regulating mechanism ensures that the sun maintains a remarkably consistent output of energy over billions of years. The sun's structure reflects this balance. In the core, where fusion occurs, temperatures reach 15 million degrees Celsius and densities exceed those of water by more than 150 times. As we move outward through the radiative and convective zones, the temperature and density gradually decrease, adjusting precisely to maintain equilibrium at every layer. Even the sun's surface, the photosphere, exists in harmony with these forces, radiating energy into space while maintaining the stability necessary for life on Earth. Without this finely tuned balance, the sun would not exist as we know it. Too much pressure, and it would swell into a red giant prematurely. Too little, and it would collapse into a white dwarf. Instead, it remains in a state of perfect tension, neither exploding nor imploding, but instead shining steadily, lighting the sky, and sustaining the delicate web of life that depends on its warmth. The sun's final act, evolution, and legacy. Though the sun has been a steady presence in our lives for billions of years, it is not eternal. Like all stars, it follows a life cycle dictated by the delicate balance between gravity and nuclear fusion. Currently, the sun is in its prime, a middle-aged star, burning hydrogen in its core and radiating energy with remarkable consistency. However, this phase, known as the main sequence, is not infinite. In roughly 5 billion years, the sun will exhaust its hydrogen fuel, setting off a dramatic transformation that will reshape its structure and redefine its role in the solar system. As hydrogen fusion in the core begins to wane, the balance between gravity and pressure will shift. Without the outward push of fusion energy, gravity will gain the upper hand, causing the core to contract and heat up. This increase in temperature will ignite hydrogen fusion in a shell surrounding the core, marking the beginning of the sun's next evolutionary stage, the red giant phase. During this period, the sun will swell dramatically, expanding outward and engulfing the inner planets, possibly including Earth. Its surface will cool, shifting from yellow to a deep reddish hue, while its luminosity will increase significantly, making it appear brighter despite its lower surface temperature. Eventually, the core will reach temperatures high enough to initiate helium fusion, transforming helium into carbon and oxygen in a process known as the triple alpha reaction. This phase will be relatively short-lived, as helium is a less efficient fuel source than hydrogen. Once helium fusion ceases, the sun will shed its outer layers in a series of gentle pulses, expelling gas and dust into space to form a glowing planetary nebula. At the heart of this ethereal shell will remain the sun's core, a dense, Earth-sized remnant known as a white dwarf. Unlike the sun's current fiery existence, this white dwarf will no longer produce energy through fusion. Instead, it will slowly radiate its residual heat into the cosmos, cooling over trillions of years until it fades into darkness as a hypothetical black dwarf. Though this final stage marks the end of the sun's active life, its legacy will endure. The elements forged in its core, carbon, oxygen, and other heavy elements, will enrich the interstellar medium, becoming the building blocks for future generations of stars and planets. In this way, the sun's story does not end with its death, but continues in the endless cycle of cosmic creation. The cosmic web, how the sun shapes our universe. The sun's influence extends far beyond its immediate surroundings, weaving itself into the very fabric of the cosmos. From the birth of planets to the evolution of galaxies, the processes that power our nearest star ripple outward, shaping the universe in profound ways. Every element heavier than hydrogen and helium, every atom of carbon in your body, every molecule of oxygen in your lungs, every trace of iron in your blood was forged in the heart of a star, like the sun, or in the explosive aftermath of a supernova. The sun itself is not just a product of this stellar recycling, but a key player in continuing it. Our solar system formed from a swirling disk of gas and dust, remnants of earlier generations of stars that had lived, died, and scattered their contents across the galaxy. The sun, igniting at the center of this collapsing cloud, provided the gravitational anchor that allowed planets, moons, asteroids, and comets to coalesce. Its heat and radiation shaped the composition of these worlds, determining where ice could form, where rocky bodies could condense, and ultimately where life could take root. Mars, Venus, and Earth owe their positions in the habitable zone to the sun's delicate balance of temperature and brightness, a balance maintained by the steady fusion reactions in its core. Beyond our solar system, stars like the sun contribute to the grand architecture of galaxies. Their light illuminates the vast cosmic web, revealing the structure of the universe on the largest scales. The energy they release influences the interstellar medium, triggering the formation of new stars and regulating the growth of galaxies themselves. In regions where massive stars explode as supernova, shockwaves compress nearby gas clouds, setting off fresh waves of starbirth. Even the sun, in its eventual death, will contribute to this cycle, scattering its enriched material into space and seeding the next generation of planetary systems. The sun is not just a solitary beacon in the sky. It is part of an intricate cosmic network, a link in the chain of creation stretching back to the earliest moments of the universe. Understanding its life, its death, and its role in the greater galactic ecosystem helps us grasp our place in the cosmos, not as isolated observers, but as participants in an ongoing story of transformation, renewal, and connection across the vast expanse of space and time. Harnessing the power of the stars. The quest for fusion energy, while the sun effortlessly harnesses nuclear fusion to sustain itself for billions of years. Humanity has spent decades striving to replicate this process here on Earth. The dream of controlled fusion energy is one of the most ambitious scientific endeavors of our time and effort to bottle the power of the stars and use it to generate clean, nearly limitless energy. Unlike fossil fuels, which release carbon dioxide and contribute to climate change, or nuclear fission, which produces radioactive waste, fusion offers a sustainable alternative with minimal environmental impact. If we can master it, fusion could revolutionize the way we power our world, providing abundant energy without pollution, resource depletion, or the risks associated with conventional nuclear reactors. Replicating the conditions of the sun's core on Earth is no small challenge. In the sun, fusion occurs under immense gravitational pressure, compressing hydrogen nuclei tightly enough for them to overcome their natural repulsion and fuse together. On Earth, we lack the luxury of solar mass and must instead rely on advanced technology to create the necessary conditions artificially. Temperatures exceeding 100 million degrees Celsius are required to transform hydrogen isotopes, typically deuterium and tritium, into a superheated plasma, a state of matter in which electrons are stripped from atoms, leaving behind a charged soup of nuclei and free electrons. But heat alone is not enough. We must also confine this plasma without allowing it to touch any physical material, as no known substance can withstand such extreme temperatures. Two primary approaches have emerged in the pursuit of fusion energy: magnetic confinement and inertial confinement. Magnetic confinement, the more mature of the two, uses powerful magnetic fields to contain and control the plasma, preventing it from coming into contact with the reactor walls. The most well-known design for this method is the tokamak, a donut-shaped device that employs superconducting magnets to stabilize the plasma in a continuous loop. The International Thermonuclear Experimental Reactor ITER, currently under construction in France, represents the culmination of decades of research in this field. Designed to be the first fusion device to produce more energy than it consumes, ITER aims to demonstrate the feasibility of fusion as a viable energy source. If successful, it could pave the way for future commercial fusion power plants, bringing us one step closer to realizing the dream of clean, limitless energy. Meanwhile, inertial confinement takes a different approach, using intense laser beams or particle accelerators to compress a tiny pellet of fusion fuel, triggering a brief but powerful burst of energy. This method mimics the rapid compression seen in astrophysical phenomena such as supernova, and while it presents significant engineering challenges, recent breakthroughs suggest that controlled fusion ignition may soon be within reach. Private companies and government-funded laboratories alike continue to push the boundaries of what is possible, refining techniques and developing new materials that could one day make fusion a practical reality. Despite the obstacles, the potential rewards of fusion energy are immense. Deuterium, one of the primary fuels, can be extracted from seawater, offering an effectively inexhaustible supply. Tritium, though less abundant, can be bred from lithium, another widely available resource. Unlike traditional nuclear reactors, fusion does not carry the risk of runaway meltdowns or long-lived radioactive waste. The byproducts of fusion reactions are primarily helium-harmless, inert gas and neutrons, which can be used to generate heat for electricity production. With continued investment, innovation, and international collaboration, fusion energy could become a cornerstone of a sustainable future, proving that the same process that powers the stars can also illuminate our world. The sun's hidden mysteries, flares, storms, and solar surprises. Beneath the sun's steady glow lies a world of unpredictable eruptions and magnetic turbulence. While we often perceive the sun as a constant, unwavering presence in the sky, its surface is in a state of constant flux, marked by sudden bursts of energy, twisting magnetic fields, and explosive solar storms. Among the most dramatic of these phenomena are solar flares, intense bursts of radiation caused by the sudden release of magnetic energy stored in the sun's atmosphere. When magnetic field lines become tangled and unstable, they can snap and reconnect in a process known as magnetic reconnection, unleashing an immense amount of energy in just a few minutes. These flares emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, and can have significant effects on Earth, disrupting satellite communications, GPS signals, and even power grids. Even more powerful than flares are coronal mass ejections, CMEs, massive eruptions of plasma and magnetic field that blast billions of tons of solar material into space at speeds exceeding several million kilometers per hour. When a CME is directed toward Earth, it can collide with our planet's magnetosphere, triggering geomagnetic storms that distort the protective shield of charged particles surrounding our world. These disturbances can generate dazzling auroras, far beyond their usual polar latitudes, painting the night sky with shimmering curtains of green and red light. However, they can also pose serious risks to modern technology, potentially damaging satellites, interfering with airline navigation systems, and inducing electrical currents that overload power transformers. One of the most famous historical examples of such an event occurred in 1859, known as the Carrington event, when a powerful geomagnetic storm caused telegraph systems across Europe and North America to fail, shocking operators and even sparking fires. If a similar event were to occur today, the consequences for our electronics-dependent society could be severe. Understanding and predicting these solar outbursts is a major focus of modern heliophysics. Scientists monitor the sun's surface using a fleet of observatories, including NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter, which provide high-resolution images and data on solar activity. By tracking the evolution of sunspots, dark, magnetically active regions on the sun's surface, researchers can anticipate when and where flares and CMEs are likely to occur. Additionally, spacecraft like the Parker Solar Probe venture closer to the sun than ever before, collecting direct measurements of the solar wind and magnetic fields to improve our understanding of how these eruptions develop. Despite these advancements, predicting the exact timing and intensity of solar storms remains a challenge, highlighting the complex and dynamic nature of Earth's sun's magnetic activity follows an approximately 11-year cycle, known as the solar cycle, during which the frequency of flares and CMEs fluctuates. During periods of solar maximum, the sun is covered with numerous sunspots, and eruptions are more frequent. Conversely, during solar minimum, the sun appears calmer, with fewer visible features. However, even during quieter phases, the sun can still surprise us with unexpected eruptions, reminding us that its behavior is far from predictable. Some historical anomalies, such as the Maunder Minimum period between 1645 and 1715, when very few sunspots were observed, have led scientists to speculate about potential links between solar activity and Earth's climate. While the relationship remains complex and not fully understood, studying these variations provides valuable insights into how our star influences the conditions of our planet. Nearest star. By unraveling the mysteries of solar flares, CMEs, and the broader patterns of solar activity, we gain not only a deeper appreciation of the sun's dynamic nature, but also a better ability to protect ourselves from its occasional outbursts. Whether it is safeguarding critical infrastructure or ensuring the safety of astronauts venturing beyond Earth's protective magnetosphere, understanding the sun's volatile behavior is essential for navigating our increasingly interconnected and technology-driven world. Unveiling the sun. Tools and techniques of solar observation. Peering into the heart of the sun is no easy task. Its searing brightness, immense distances, and complex layers of plasma present formidable challenges to direct observation. Yet, through ingenuity and technological advancement, Scientists have developed an array of tools and techniques to study our nearest star in unprecedented detail. From ground-based telescopes equipped with specialized filters to spaceborne observatories capable of capturing high-resolution images in multiple wavelengths, our understanding of the Sun has expanded dramatically in recent decades. One of the most iconic instruments in solar observation is the Solar and Heliospheric Observatory, SOHO. Launched in 1995 as a joint mission between NASA and the European Space Agency. Positioned at the Lagrange point 1, approximately 1.5 million kilometers from Earth, SOHO provides an uninterrupted view of the Sun, allowing scientists to track solar activity ranging from sunspots and flares to coronal mass ejections, equipped with a suite of instruments. SOHO has been instrumental in advancing helioseismology, the study of sound waves traveling through the Sun's interior, much like geologists use seismic waves to probe Earth's internal structure. Helioseismologists analyze these oscillations to infer details about the Sun's hidden layers, including the behavior of plasma flows and the rotation of different regions. Building upon SOHO's success, NASA's Solar Dynamics Observatory SDO, launched in 2010, has taken solar imaging to new heights. SDO captures ultra-high-definition images of the Sun in multiple wavelengths of extreme ultraviolet light, revealing the intricate dance of plasma and magnetic fields in the chromosphere and corona. Its instruments produce over a terabyte of data daily, enabling researchers to study solar dynamics with unparalleled precision. Time-lapse videos constructed from SDO's observations showcase the Sun as a living, breathing entity. Loops of plasma arc across the surface, flares erupt with explosive force, and the entire disk pulsates like a drum. Yet, even the most detailed images from a distance cannot replace the insights gained from direct exploration. Enter the Parker Solar Probe, a groundbreaking mission launched in 2018 with the audacious goal of touching the Sun. Designed to withstand temperatures exceeding 1,400 degrees Celsius, the probe ventures closer to the Sun than any spacecraft before it, flying within just over 6 million kilometers of its surface. Armed with cutting-edge instruments, the Parker Solar Probe investigates the solar wind, the stream of charged particles flowing from the Sun into space, and measures the structure of the solar corona. Already, it has provided answers to long-standing questions, such as why the solar wind accelerates dramatically as it leaves the corona and how the Sun's magnetic field behaves in the outer atmosphere. Complementing Parker's daring approach is the European Space Agency's Solar Orbiter. Launched in 2020, while Parker dives in close, Solar Orbiter maintains a more distant orbit, allowing it to observe the Sun's poles regions, difficult to study from Earth. Understanding the polar magnetic fields is key to unraveling the mysteries of the solar cycle and predicting solar activity. Together, these missions form a kind of cosmic observatory, each contributing a unique perspective that enhances our collective knowledge of the Sun. Ground-based observatories also play a critical role in solar research. Instruments like the Daniel K. Inouye Solar Telescope in Hawaii utilize advanced adaptive optics to compensate for atmospheric distortion, achieving resolutions as fine as 30 kilometers across the Sun's surface. These observations reveal minute details of sunspot structures, convection cells, and magnetic field interactions, offering insights into the mechanisms driving solar activity. Beyond visual observations, scientists employ indirect methods to study the Sun's interior. Helioseismology, as mentioned earlier, uses vibrations on the Sun's surface to map its internal structure. Similarly, neutrino detectors located deep underground, such as the Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada, monitor the ghostly particles produced in the Sun's core, shielded from cosmic rays and background noise by kilometers of rock. These detectors capture fleeting interactions between neutrinos and detector materials, providing direct evidence of ongoing fusion reactions in the sun's heart. Through this diverse arsenal of tools and techniques, scientists have pieced together a comprehensive picture of the sun's dynamic nature. Each observation contributes to refining our models, improving predictions, and uncovering new mysteries. Whether watching the sun's surface from afar, diving into its atmosphere with robotic probes, or listening to its vibrations like a cosmic heartbeat, humanity's quest to understand the star that never sleeps continues to yield discoveries that illuminate both the universe and our place within it. As we bring our journey through the wonders of the sun to a close, we find ourselves gazing at the same celestial body that has inspired awe for millennia. The sun, ever-present and ever-changing, is more than just a glowing orb in the sky. It is the architect of life, the engine of our solar system, and the silent witness to the unfolding of cosmic history. From the moment it ignited in a cloud of interstellar dust to its current golden age of steady fusion, the sun has been a beacon of energy and transformation. And though it will one day evolve into a red giant and eventually fade into a white dwarf, its legacy will endure in the elements it forged, the planets it shaped, and the life it nurtured. Every beam of sunlight that touches our world carries with it the echoes of nuclear fusion, a process so fundamental, yet so extraordinary, that it powers not just our star, but all the stars in the universe. The warmth on your skin, the light filtering through your windows, the very air you breathe, all of it is a gift from the sun's relentless, patient work. In its quiet brilliance, it reminds us of the delicate balance that sustains existence, the intricate dance of forces that governs the cosmos, and the enduring wonder of the universe we call home. So, as you step outside tomorrow morning and feel the sun's familiar embrace, take a moment to reflect on the vast unseen processes unfolding above you. Behind that golden glow lies a story written in fire, light, and time, a story that connects us to the stars, to the past, and to the boundless possibilities of the future. The sun never sleeps, and neither does the curiosity that drives us to understand its secrets. Drifting off under the sun's eternal glows, the day draws to a close, and the last golden rays of sunlight stretch across the horizon. There is a quiet comfort in knowing that the sun never truly rests, even as we settle into the hush of evening. It continues its tireless work, converting matter into light, sending warmth across the vastness of space, and shaping the rhythms of life on Earth. There is something profoundly soothing about this unbroken cycle, this steady presence that has guided civilizations, warmed oceans, and painted the sky with color since long before we were here to witness it. Perhaps tonight, as you lie beneath the blanket of darkness, you'll find yourself thinking back to the journey we've taken together, from the turbulent heart of the sun's core to the flickering dance of solar flares, from the ancient birth of our nearest star to the future it holds in store. Maybe you'll imagine the photons that left the sun eons ago, only now arriving to kiss your skin, or the neutrinos that slipped through your body unnoticed, carrying messages from the very heart of fusion itself. Perhaps, as sleep gently takes hold, you'll feel a quiet sense of connection, knowing that the same energy that lights the stars also courses through you, linking you to the vast and endless tapestry of the cosmos. If this journey has stirred your curiosity, if it has given you a moment of wonder to carry into your dreams, then I hope you'll join me again soon. The universe is full of stories waiting to be told, and there is always more to explore. Until next time, may the sun's steady glow guide you into peaceful rest, and may its light greet you anew with the promise of another day filled with discovery. Where are you watching from, and what time is it there? I'd love to know in the comments. It's always a joy to see where in the world you're listening from. If this helped you unwind or sparked a bit of curiosity, feel free to like the video and subscribe for more calm/thoughtful science stories to fall asleep to. Wishing you a warm, peaceful night lit softly by the star that never sleeps, the ever-burning heart of our world.